We have, imagine a race car that is traveling down a track. That race car is at some position at some point in time, some initial point in time, and it has some speed there. It's continuing to accelerate, so it's going faster and faster and faster as it goes down the racetrack. And so at some later point in time, it's at some position farther down the track, and it has some velocity that's greater than its earlier velocity because it has accelerated. And so remember the relationships that we have. The velocity is the rate of change of position, or the integral of the velocity gives us the displacement over a certain time interval. The acceleration is the rate of change of the velocity, or the integral of the acceleration gives us how much the velocity has changed in a certain time interval. So in this case here, we're assuming constant acceleration of this race car as it travels down the track. And so if we have constant acceleration, we'd expect the acceleration to be constant if we look at the acceleration graph, which means that it's going to be a horizontal function. As time goes on, the value of the acceleration stays constant that whole way. So what we can do is we can take the antiderivative of the acceleration, we can integrate this acceleration function to find the velocity. If this is a constant function, then the integral of a constant function would be a linear function. And so our velocity here is a linear function. And then we said that if you integrate the velocity, that gives you your displacement. You can use that to find your position. So if we integrate a linear function, that gives us a quadratic or a parabolic function. And so we can see here that x should go like t squared. Our velocity should go like t, it should be linear, and that our acceleration is going to be constant, is the primary assumption of what we're going to look at here. So let's look a little closer at the situation. Again, we're assuming that we have a race car, and we're assuming that this race car is traveling down a track, that at some initial point in time, it has some initial position. At some final point in time, it has some final position. It has a constant acceleration over the course of this motion, and as it accelerates, its speed is increasing from some initial velocity to some final velocity. And this is the important assumption for us. We have some interval here, and the key part is that we have constant acceleration over that interval. So we start at a place in time, we end at a place in time, we start with some velocity, we end with some other velocity, and the thing that connects these two ends of this interval is that the acceleration is constant throughout that whole interval. And a constant acceleration means that we'd have a horizontal acceleration function. And so we know that our acceleration is defined as the rate of change of the velocity. That's going to be our derivative of the velocity. And again, our assumption here is that the acceleration is constant. And so we can undo this integral, or we can undo this derivative with an integral to figure out what the velocity would be given this acceleration. So what we can do is multiply both sides by dt. The dt's will cancel here. And what we have now is this. I have two differential terms, so to undo those, I can integrate both sides. I'm going to integrate from t0, the beginning time, to some final time. And I can integrate my velocity from my initial velocity at the beginning of this interval, and I'm going to integrate to some final v. And what I'm doing here is I'm leaving t to be some arbitrary t. I'm leaving v to be some arbitrary v. Implicitly, this v is a function of time, because depending on where we cut off the end of our interval here, we're going to have a different velocity depending on how long we allow this constant acceleration to go on for. If I integrate dv, and in fact, I should prime my variables of integration here. If I integrate dv prime, I should just get v prime. And I'm going to evaluate that from v0 to v, from some constant value that's my starting velocity to some arbitrary final velocity, depending on where I cut off my interval. And if I integrate dt prime, I'm going to get t prime. The acceleration here is assumed to be constant, so that's not going to affect the integral. That acceleration is just going to sit there. And I'm going to evaluate at those 2 points there. When I evaluate my endpoints here, I'm going to have v minus v0. And technically here I'd have t minus t0, but typically what we'll do is factor out the acceleration here as a common term, and we'll have this equation. And so I can say v is v0 plus a times t minus t0. This v here is implicitly a function of time, and I can have my velocity as a function of time. If I know my starting velocity, I know my starting time, and I know the acceleration. Again, all of this assumes we are in the x direction. All that we're in one dimension here. If I know my starting velocity, I know my starting time, and I know my acceleration, I can figure out what my velocity would be at any point later in time by evaluating at that value t. You see in this equation here, it's the same thing, but oftentimes this term is simplified into a simple delta t, the time interval across which we have this constant acceleration. We can revisit the same situation where we have our velocity as a function of time here, and we want to take this a step further and figure out if we know what the velocity is, we can hopefully figure out what the position is. Again, remember, this is the initial velocity at the beginning of this interval of acceleration, so this is a constant fixed value. This was the speed at some point in the past, so we can measure that and we know exactly what it is. This is the acceleration. We know that this is a constant value because that's the entire assumption behind our constant acceleration. And t0 is the time of the beginning of the interval of acceleration. Oftentimes, this term here is reduced to a delta t, but for right now, since we're dealing with this as a function of t, we want to be able to see the t there in that function. So we have our velocity here, and we recall that velocity is the derivative of position. So we should be able to say that this velocity here is going to be the derivative of the position function representing the position of that race car as it goes across an interval of constant acceleration. So same thing as before, I can multiply both sides by dt, and we can look at what we have. So here we have a relationship between our variables. What we want to do is figure out what the position is, so we're going to integrate both sides to get rid of these differential terms. Since we're integrating, I'm going to make these primed variables so that these are my variables of integration. My position is going to go from my starting position to some final position. This position is implicitly a function of time. It depends on, again, how long we make this interval of constant acceleration to go on. These are the endpoints for my position. They have to agree with my endpoints for time. The time of this integral starts at t0. T0 is the beginning of the interval of acceleration, and we're letting it go to some final value of t. So depending on how long I allow the interval to be, depending on what value of this time t I pick, I'm going to have a different value of x associated with it. That's why this position is a function of time. That's also why I'm using the primed variables. So as long as I have primed variables, I know I haven't taken the integration yet. Once I take the integral, I'm going to evaluate with the regular t, and I'll replace my t prime with a t there. So I'm going to go ahead and perform these integrals. Looking at this part here, I have two terms. I'm going to integrate these two terms separately. The first one is just a constant. So if I integrate this constant with respect to dt prime, then I'll just get this relationship here. In this case, I have a t prime. I could distribute this if I wanted to, but basically what I'm going to do is do a u/du substitution. And you'll see that I'm essentially integrating u, which gives me u squared over 2. And so what I'm actually going to get there is u squared over 2. This is the 1/2, represents that over 2. And I got u squared, where u is that quantity that I have there squared. So again, this is my u squared over 2 that I get from that integral. And I'm going to evaluate that from t0 to t as well. When I plug these values in, I get these things. I evaluate with t prime equals t, and I subtract, and I plug in the other endpoint for my t prime. And notice what happens here. This term goes away. And so what I have here is my final position as a function of time. My final position depends on my starting point. It depends on how fast I was going at the beginning and how far I would have traveled due to that initial time, plus a term representing how much my velocity has changed due to the acceleration I'm experiencing, and that will affect how far I travel as well. Oftentimes, x final minus x initial is called delta x, our displacement, that's that term there, and our t minus t0 is often called delta t, that is the time increment, that's the time that elapses as this segment of constant acceleration goes on. But what I've done here again is I've derived another equation here representing the displacement of a race car, but really the displacement of any object as it undergoes constant acceleration. If I know how long this constant acceleration is going on for, if I know how fast the object was going at the beginning, I can figure out how fast it will have gone. And since this is generalized, this is true for any object undergoing constant acceleration. So I don't have to rederive this every time. I can just use this equation that I've derived. I also have an equation as a function of time in case I want to do further calculus for some reason. Another way to approach this is graphically. In this graph here, we have a constant slope of our velocity versus time graph. So a constant slope means a constant change in velocity, which is our acceleration. That's the whole assumption that we're making. So if we have a constant acceleration, we're going to have a linear velocity, and our graph would look something like this. At our initial time, we would be at some initial velocity, and at our final time, we would be at some final velocity. And so if we want to know our displacement is the area under the curve, because the derivative of position is velocity, and so the integral of the velocity is our change in position, that is our displacement. So that's this area under the curve. Our displacement is the area under the curve. And this area here is a trapezoid. It has one set of parallel sides, and then the other pair of sides are not parallel. So that's a trapezoid. And if we want to find that area, the equation for the area of a trapezoid is 1/2 the sum of the bases times the height. So the bases are the two parallel sides, and then the height is how far apart those parallel sides are. In this case, the two bases are this side, which is V0, and this side, which is Vx. So base 1 is V0, and base 2 is Vx, the final velocity and the initial velocity. And the height here is the time. It's this height is the distance between the initial and final velocities on that graph. And so all of that together, this total area, is the area under the velocity graph is our displacement. So our displacement during during a portion of our constant acceleration would depend on the initial and final velocities and how much time elapses. What this equation is saying in general is that our displacement is our average velocity per time, because for the specific case of constant acceleration, the average velocity is the initial and final velocities divided by 2. I want to make a strong note here. This is not generally true. It is only true for when we have constant acceleration. But what we have here is another relationship between how far we've traveled during this interval of acceleration, how much time this interval of constant acceleration has lasted, and our initial and final speeds during this interval. And finally, we can approach this same relationship one more time. Again, we're assuming that the acceleration is going to be constant. That's the primary assumption of everything that we have looked at here. And we say that the acceleration is the derivative of the velocity, the time rate of change of the velocity. But what we can do is use the chain rule here, and we can multiply by dx over dx. We can group these terms so that we have something that looks like this instead. Furthermore, we can notice that dx over dt is the definition of the velocity. So we can say that dv dx times the velocity, this function here is equal to the acceleration, which is constant. And so we still have a differential equations here. We still have a equation that we can solve. We have two differential terms, so we have to multiply both sides by dx, and that will cancel there and there. I'm going to reorder these two. And again, I have two differential terms. I want to get rid of those, so I'm going to integrate both sides to get rid of the derivatives. I have to integrate my position from x initial, x0, to some final value of x. And I'm going to integrate my velocity from some initial velocity to some final velocity there. When I integrate, a is a constant. It's the constant acceleration. So this is just going to sit there. If I integrate dx, I get x. The constant value is just going to sit there. I'm going to evaluate at my endpoints. Here, I have a velocity. I have v dv. And so if I want to integrate v dv, I do my standard integration. Integrating v dv gives me v squared over 2. Technically, prime my variables of integration here. So if I integrate v prime dv prime, I should get v prime squared over 2. I'm going to evaluate at my endpoints. What happens here, generally this is represented as the displacement, delta x. This is the final position minus the initial position, so this is the displacement, how far we've gone during this interval of constant acceleration. What else we do is we multiply through by 2. So this 2 is going to cancel here and cancel there, and we get a factor of 2. And so we have and then finally we can solve for, be careful to distinguish your subscripts from your full values. But what I can say here is that my final velocity squared is equal to my initial velocity squared plus 2 times the acceleration times the displacement that I undergo across that interval of constant acceleration. And so this velocity here is again implicitly a function of x, because depending on how far we go in our interval of constant acceleration, depending on the distance we travel, that's also how much we're going to speed up as we go across that interval. And so we get v as a function of x because we rewrote v as a function of t into being v as a function of x. In fact, what's happening here is that v is a function of x, but x is itself a function of t. So that's how we can use the chain rule to represent. We can think of v as being a function of t, or v depending on x, but we realize x is also a function of t. When we put all this together, we have these kinematic equations. They're also called the constant acceleration equations, because the whole assumption that we used was that we have constant acceleration over this interval of acceleration. We assumed a race car that was starting at some initial point at some initial point in time with some initial speed. It accelerates over an interval of constant acceleration, and at the end of that, it has a final speed. Some time has passed, and the car has undergone a displacement. But we can generalize this. These same derivations are true for any object undergoing constant acceleration. We realize that there are 5 variables that we've seen. There was v initial and v final, the velocity at the beginning of the interval and the velocity at the end of the interval. There's an acceleration over that interval that's assumed constant, and we have a displacement in space and a elapsing of time. Each one of these are x minus x0 and t minus t0, respectively. And so sometimes we deal with these as functions of time, but really a lot of times we deal with these as just the total distance and the total time. We have derived this equation, this equation, this equation, and this equation. We can see that this one is related to the other ones, and I will leave that to you to derive on your own. Notice that we end up with 5 constant acceleration equations to match the 5 constant acceleration variables that we have. Each one of these 5 equations has 4 of the 5 variables present in it. Each one of these equations is missing one of those variables. And so for any given situation, you can look at what you know and what you're trying to find, and there's an equation that you'll be able to use whatever values that you know and to find whatever value you're trying to find while getting around a lack of information about one specific detail or another. Just to recap constant acceleration, this is motion with constant acceleration, what a motion diagram would look like. Notice that we have a constant acceleration vector along each particle. Because we have a constant acceleration, that means that the velocity vectors are getting longer. There's an equal increase in length from here to here, and there's the same increase in length from there to there. There's the same increase from length from there to there because we have a constant acceleration. And because the velocity vectors are getting larger, that means that our object is moving a greater distance in the same amount of time. If we look at the graphs, a constant acceleration, any constant function shows up as a horizontal line. The derivative, or the velocity, is the integral of the acceleration. So and the acceleration is the derivative of velocity. So a constant derivative means a constant slope, and our velocity is a straight line. The position is the integral of velocity. So if we integrate a linear function, we get a quadratic or a parabolic function. Thus far, what is assumed is a positive velocity, positive acceleration. That was what we assumed to set up our equations. The equations that we used do not require that. The equations that we've used are true whether the acceleration is positive or negative. In this case, we have a negative acceleration, and so a negative acceleration means a negative slope of the velocity. So the velocity is angled downwards, but it's still a constant, or it's still a linear velocity and still a linear acceleration. In this case, we have a parabolic position, but we have a concave down position function, which means that which corresponds to a negative acceleration, a negative second derivative. And then finally, we have the acceleration has to be constant over a given interval. Notice here the acceleration is not constant everywhere, but the acceleration is constant over this interval and over that interval. And so we can break everything else up along those same intervals as well. And we can see here that we have a constant acceleration, so we have a linear velocity, we have a parabolic position. Here we have zero acceleration. Zero acceleration means uniform motion. In this region here, we have zero acceleration, so we have constant velocity in that interval, and then we have a constant slope for the position function during that interval. And then for a new interval here, we have a new constant acceleration, we have a new slope to our velocity graph, and we have a new curvature of our position graph. So we can take any motion, and if we have multiple intervals, we can treat each interval as constant acceleration. We know that the final velocity at the end of this interval would be the beginning velocity at the beginning of this interval. The final velocity at this interval would be the beginning velocity of the next interval, and so forth. Since we started at acceleration, the velocity has to be continuous, because if we are integrating the acceleration to get velocity, we are adding up the space under the curve, and we have to have a continuous amount of space being added. We can add or subtract area under the curve, but the total sum of the area under the curve has to be continuous the whole way. The position function is a double integral. We integrate acceleration to get velocity, we integrate velocity to get position, so the position curve has to be continuous and differentiable. So the position curve has to be continuous and smooth. Notice how the slope from one section here goes smoothly into the next section. The slope from this section goes smoothly into that section. There's no kink there, the way that we have a slope here and then a sudden change in slope there. Here the velocity is only continuous, even though we have a change in slope at each one of these places. Here we are continuous, but also notice that the slopes are the same.